Hello everybody, getting ready to do lesson 2.4 part 1 classwork today of pre-calculus math. If you need note-taking guides or solution PowerPoints, email me here. And today we got 2.4 complex numbers, part 1. We got 70 points here of classwork, so note-taking guide would really be nice. For this lesson, you got 4 points here to go into your notebook. And teachers, today's bell work is perform the operation and write the result in standard form here. Students, so you got a cube of that, and then you multiply these binomials. Teachers, give your students about 5 minutes. Okay, welcome back for solutions of today's bell work. So up here, when you multiply these two binomials together, you got a difference here of a square, so your middle term goes away. So it's 16x squared minus 25 for when you multiply these two together. Down here, you got a cube here, and then the pattern for a cube, x cubed, and then was it 2 times ab? So it'll be 3x squared times 2 plus 3x times 2 squared and plus 2 cubed, and this simplifies down to x cubed plus 6x squared plus 12x plus 8 for this cube here. Okay, into our first page here, the imaginary unit I. Some quadratic equations have no real solutions. So the quadratic equation like this, x squared plus 1 equals 0, has no real solution because there is no real number x that can be squared to produce a negative 1. To overcome this deficiency, mathematicians create an expanded system of numbers using the imaginary unit I, defined as I equals the square root of negative 1, and where I squared equals negative 1. By adding real numbers to real multiples of this imaginary unit, you obtain a set of complex numbers. Each complex number can be written in the standard form a plus bi. For example, this of the complex number of square root of negative 9 minus 5 is negative 5 plus 3i, because the square root of negative 9 minus 5 equals the square root of 3 squared times negative 1 minus 5. So when you put it into this form here, the 3 will go outside the radical, and now you have a square root of negative 1 minus 5. Then the square root of negative 1 is I, so 3i minus 5, and then put it into standard form. Here will be negative 5 plus 3i. So in the standard form, a plus bi, the real number a, is called the real part of the complex number a plus bi, and the number bi, where b is a real number, is called the imaginary part of the complex number here, a plus bi. So this is real, and then this is the imaginary part. So definition now of a complex number. If a and b are real numbers, then the number a plus bi is a complex number, and it is said to be written in standard form. When it's like this is standard form. If b equals 0, then the number a plus bi, a is a real number. It would just be a real number. If b does not equal 0, then the number a plus bi is called an imaginary number. A number of the form bi, where b does not equal 0, is called a pure imaginary. So where b does not equal 0, number of the form bi. So if it's just bi, that would be a pure imaginary. It wouldn't be a complex number. For every real number a, you can write a equals a plus 0i. So real numbers and imaginary numbers, when they come together, they become a complex number. So the equality of complex numbers. Two complex numbers, a plus bi and c plus di, written in standard form are equal to each other. So a plus bi equals c plus di is an equality of two complex numbers if and only if a equals c, and b equals d. If b equals d and a equals c, then they are equal to each other. Operations with complex numbers. To add or subtract two complex numbers, you add or subtract the real and imaginary parts of the numbers separately. So, like here, a plus bi and c plus d are two complex numbers written in standard form. Then their sum and difference are defined as follows. So the sum here, a plus bi plus c plus di equals a plus c. So we add by grouping here, plus b plus d multiplied by I. And then you do the same thing here with a difference. You group together your reals and then you group together your imaginaries. So that would be the way that you would do these to manipulate addition and subtraction of complex numbers. The additive identity in the complex number system is 0, the same as in the real number system. Furthermore, the additive inverse of the complex number a plus bi is the negative of a plus bi, which equals negative a, negative bi. This would be the additive inverse of a plus bi. So you have a plus bi plus the negative a minus bi equals 0 plus 0i, which would equal 0. That'd be your additive inverse. Let's go on to an example now. Adding and subtracting complex numbers, perform the operations, and write the result in standard form. So we have 3 minus I plus 2 plus 3i. So the way to do that would be our standard method of adding the two complex numbers. 3 minus I plus 2 plus 3i is the same thing as 3 minus I plus 2 plus 3i. Remove the parentheses. Group like terms here, 3 plus 2, and then negative I and 3i. And then when we combine these two different groups together, you have 5 plus 2i. That's written in standard form. And then b up here, 1 plus 2i minus 4 plus 2i. So when you subtract these two complex numbers, now we have 1 plus 2i minus 4 minus 2i. And then we group together our two reals here, 1 minus 4. And then we add our 2i minus 2i. We group like terms. Then when we do that, we come up with negative 3 plus 0i. So it's just negative 3 here for when you combine those two complex numbers together here. And then c, we have 3 minus a negative 2 plus 3i plus a negative 5 plus I. So we have this big thing here, and then we take away our parentheses. We're going to group like terms here now, so 3 plus 2 minus 5 plus negative 3i plus I. And then when we do our addition here, we have 0 minus 2i. Here, 0 minus 2i. And then we just get rid of 0, we have minus 2. So d, 3 plus 2i plus 4 minus I minus 7 plus I. So we have this big long thing here. We take away our parentheses. We have this array here. And then we group together our real numbers here. And then our imaginaries over here. So this comes up to 0. This comes up to 0. So it equals 0. 0 plus 0i is 0. So let's go into a guided practice here. Perform the addition or subtraction and write the result in standard form. 13i minus 14 minus 7i. We'll do that one. Students, this is yours down here. Do that one on your own. Okay, up here we have this was the initial here. And then we're going to take away the parentheses. 13i minus 14 plus 7i. And then we just combine here. And we have a negative 14 plus 20i. Then down here I threw this one in. This is what you should get down here for your addition down here, combining your complex numbers down here. 22 plus a negative 5 plus 8 minus 9 times I. That will be 17 minus I. Okay, many properties of real numbers are valid for complex numbers as well. Here are some examples. So we have associative properties of addition and multiplication, commutative properties of addition and multiplication, distributive property of multiplication over addition. Notice how these properties are used when two numbers are multiplied. So here we have, we use the distributive property here. We're going to multiply A times this, and then BI times that. And then when we do that, we come up with AC plus AD multiplied by I here. AD multiplied by I. Then over here we have BC times I plus the BD times I squared. So this one over here. Again, distributive property, and then AC plus AD times I plus BC times I plus BD times negative 1. This becomes negative 1 out here. And then when we combine like terms after we do our multiplication, we have AC minus BD plus ADI plus BCI is what we come up with here. This becomes negative BD, which is over here. Commutative property, change the order, and then we can group together now. Our imaginaries are over here, then our reals are over here. Okay, so that's similar to multiplying two polynomials and combining like terms, as in the FOIL method. That's all that is. Let's go into an example now by using that. Perform operations, write the result in standard form. 5 times quantity negative 2 plus 3i. So when we do that, we have 5 times negative 2 plus 5 times 3i, distributive property. And then we come up with this, negative 10 plus 15i. And then for B here, we got to FOIL those. So when you FOIL them out, we're going to multiply here by a distributive property. 2 times 4 plus 3i minus I times 4 plus 3i. Then we come up with this here, a plus 6i minus 4i minus 3i squared. And then this becomes 8 plus 6i minus 4i minus I squared becomes negative 1. Then when we continue to group like terms, we group these together, then we combine like terms. And this is written in standard form from up here. Then we have C here again, we get to FOIL that. We come up with this, we're going to multiply by using the distributive property, and then we come up with this sum down here, 3, 9, minus 6i, blah, blah, blah. Now our I squared is going to become negative 1, and then we continue to combine like terms, 9 plus 4, and then that's our simplification of that. So it becomes 13. This all becomes 13, written in. And then D here, 4i times quantity negative 1 plus 5i. So we're going to use a distributive property here. Then negative 4i plus 20i squared. This is going to become negative 1. And then you combine like terms out here. Negative 20. Why? Well, what do we have here? Negative 20, 20 times negative 1, negative 20, and then minus 4i. And then that's written in standard form. Then we have E here. 3 plus 2i squared. And then we come up with this, 6 plus 6i plus 6i plus 4i squared. Product of two of binomials. Then we combine, this becomes negative 1 here. 9 plus 12i plus 4 times negative 1. I squared equals negative 1. And then we have 9 minus 4 plus 12i, because this is negative 4 now. Group like terms, and then this simplifies into 5 plus 12i. Okay, let's try an example here. 1 plus I, a quantity, plus 3 minus 2I. We got two binomials here. So when we multiply these out, we're going to multiply by a distributive property. We have 3 minus 2I, 3 minus 2I, and then we have 3I, 3I minus 2I squared, and then this will become 3 plus I, negative 2I, and 3I would be I. And then negative 2 times negative 1 will be positive 2. Combine like terms, we get 5 plus I. Okay, into page 6 here of our classwork. Complex conjugates. So notice in example 2, see that the product of two complex numbers can be a real number. This occurs with pairs of complex numbers of the forms a plus bi and a minus bi, called complex conjugates. A plus bi times quantity a minus bi equals this situation here, and then a squared minus abi plus abi minus b squared I squared. A squared minus b squared times negative 1, so it becomes a squared plus b squared here. And negative abi and abi, they cancel each other out, and then you're left with this thing here. So let's try this. Another example here. Example 3, multiplying conjugates. Multiply each complex number by its complex conjugate. So 1 plus I, the complex conjugate of 1 plus I is 1 minus I. So 1 plus I times quantity 1 minus I equals 1 squared minus I squared. So we have this situation here where I squared becomes negative 1. So we have 1 minus negative 1 would equal 2. Then 3 minus 5i. So the complex conjugate of 3 minus 5i will be 3 plus 5i. So when we do that, we have 3 minus 5i here, then 3 plus 5i. When we multiply these together, we get 3 squared minus 5i squared. And of course, that would equal 9 minus 25i squared. 5i squared is negative 25i squared, which equals 9 minus 25 times negative 1, which would equal 34 for this situation here. Let's try one. Okay, 4 plus 3i. Write the complex conjugate of the complex number, then multiply the number by its complex conjugate. So we have 4 plus 3i. Down here, students, this is yours, 7 minus 5i. So 4 minus 3i is a complex conjugate of 4 plus 3i. Here, 4 minus 3i. So when we multiply these two together, we have 16 plus 9 for 16, negative 12i, positive 12i, and then negative 9i squared, which becomes negative 9. 16 plus 9 equals 25. Okay, to write the quotient of a plus bi and c plus di in standard form, the quotient now, where c and d are not both 0, they're not both 0, multiply the numerator and denominator by the complex conjugate of the denominator to obtain, like this situation here. So we have a plus bi over c plus di. So we're just going to cancel out this denominator. We're going to rationalize the denominator is what we're going to do. So to do that, we're going to multiply our numerator by the same thing that we multiply the denominator. Basically, this is 1. That's using the identity property multiplication. So multiply numerator and denominator by a complex conjugate of the denominator. So when we do that, we have AC plus BD over C squared plus D squared plus BC minus AD over C squared plus D squared all times I. This is standard form. of a complex number here. We're going to combine our reals, and then we're going to keep our imaginaries over. Okay, write the quotient of 2 plus 3i over 4 minus 2i in standard form. So when we do that, we need to multiply. We need to get rid of this 4 minus 2i here. So we're going to multiply this by its conjugate, which is 4 plus 2i. So when we do that, we have 16 minus 4i squared in the denominator, and then in the numerator we have this thing up here. Expand it out after we do our multiplication. Then we have 8 minus 6 plus 16i over 16 plus 4, meaning I squared here becomes negative 1. This becomes positive. Then when we do that, we end up with this, 2 plus 16i over 20. That's simplified out, and then this would be our complex number here, written in standard form. Now, going into this, 2 plus I over 2 minus I, write the quotient in standard form. So when we do this, we're going to multiply this by our conjugate, which is this over here, 2 plus I, and then multiply your numerator by 2 plus I. So we end up with 4 plus 1. This comes out to being 4 plus 1. And then we have our numerator, 4 plus 4i plus I squared. I squared becomes negative 1. So this is 3 plus 4i over 5. And then we separate it off here, 3 over 5 plus 4 over 5i. This is written in standard form. And that is your lesson for today in pre-calculus math. Note-taking guides, quizzes, tests, solution PowerPoints, email me here. Thank you very much.